Have you ever wondered how a drone works? Well, a drone works with the same physics properties as your everyday fan does. This particular property is called lift, and here's how it works in a single wing. Here we have the basic shape for a wing. On any moving wing, the air flowing underneath takes a shorter path than the air flowing on top. Because the air on the bottom travels a shorter distance than on top, it arrives at the back of the wing before the air on top does. This would create a vacuum towards the end of the wing, but in order to negate this, the air on top of a wing moves faster than the air on the bottom. Because of the difference in airspeed, the air on the bottom exerts more force on the wing than the air on the top does. This phenomenon is called the Bernoulli effect, a topic that you will learn more about later on in physics. This difference in pressure exerts an upward force on the wing, and we know this as lift. In order to know the force lift exerts, we use this one equation.
Lift equals 1/2 times the coefficient of lift times velocity squared times the air density times the wing area. Obviously, if we want to calculate anything with our own drone, we need to find this coefficient of lift. But what is it?
Well, it happens that the coefficient of lift is a special variable that depends on a number of other factors regarding the wing. So today we're going to find out what the coefficient of lift is for our particular drone. The variables that we need to find are the total lift our drone produces, the linear velocity of the wings as they spin, and the total surface area of the wings.
Using strobe lights, we can find the revolutions per minute of the propeller.
We can use these two equations to convert the RPM to linear velocity. So we can find that the surface area for one blade is 0.0015 meters squared. But remember that on our drone, there are 8 total blades. So we have to multiply this area by 8.
But now we're only missing one final variable, the total force of lift for our drone. In order to find this, we're going to set up an experiment involving our drone.
To find the total lift our drone produces, we attached our drone to a force sensor.
Putting our drone at full throttle, we recorded the force produced in the upward direction.
Using the readings from the force sensor, we then have to remember that just hovering in place requires the drone to overcome the force of gravity.
Finding the mass of the drone and the string attached, we were then able to calculate the force of gravity exerted on the system.
Adding all of these up, we got the total force of lift to be 1.53 newtons.
If we look again at the equation to relate angular velocity to linear velocity, we see that it's dependent on radius. This means that every point of the wing has a different velocity, and therefore every point on the wing generates a different amount of lift. To reconcile this, we need a way to add up amounts of lift at every single point on the wing. Luckily, in calculus, there's an operation to do just this. It's called an integral. You'll do this later in a more advanced math class. An integral is a way that mathematicians add up an infinite amount of infinitesimally small parts between two finite points. For our equation, we have these two finite points to be beginning and end of a wing's blade.
Calculating the integral, we get 18.186, and to get our coefficient of lift.
Now, we found our coefficient of lift for our drone. And there you have it. Now you know a little bit more about how the physics of drones and lift works. Thanks for watching. Bye!